Welcome to the final video or Unit 2, and it's the payoff. This is where the network learns the complete 10-step training pipeline: forward propagation and the cross-entropy loss, backpropagation, where the error flows backward through the layers, and gradient descent, the blindfolded walk down the mountain. By the end you'll chant the 4-beat rhythm of all deep learning: forward loss, backward update. Let's finish strong. Now let's train this thing. The full pipeline has 10 steps. Here are the first 5, the forward half. Step 1, get the inputs. Step 2, initialize weights and biases randomly. Random, because the network knows nothing yet, training will fix them. Step 3, each hidden neuron receives input from every neuron in the previous layer, computes its weighted sum, applies its activation. Layer by layer, the signal flows forward. Step 4, the output layer produces the actual output, the prediction. Step 5, compare prediction with the expected output, and compute the LOSS, the quantified wrongness. Note what an untrained network is: random weights, random guesses. A digit classifier starts at 10% accuracy, pure chance. Every point above chance will be earned by the backward half, which is next. Steps 6 through 10, the backward half and the rest of the model's life. Step 6, backpropagation, compute the gradient of the loss with respect to every weight and bias in the network. Which knob, turn which way reduces the error. Step 7, iterate. Forward pass, loss, backward pass, update repeated for a fixed number of epochs, or until convergence. Step 8, evaluate the trained model on a separate validation or test set. Part 1's data hygiene back in action. Step 9, measure with the right metric accuracy, mean squared error or F1 score, depending on the task. Step 10, deploy the model faces the real world. Here's the payoff of memorizing these 10. This list is exactly what happens inside model.fit in Keras or PyTorch. Learn the steps and every framework's code becomes readable. The next 4 slides zoom into the 2 technical hearts: forward propagation and backpropagation. Zooming in, the forward pass and the loss that judges it. Forward propagation, data flows input, 2 hidden layers to output. Each neuron does its 2-step dance: weighted sum, activation. At the end, sigmoid or softmax produces the prediction y hat. Then the loss function compares y hat with the truth. For binary classification, the standard is binary cross entropy on screen. Let's feel how it behaves. Truth is 1, the model says 0.9 confident and right. Loss negative log or 0.9, about 0.1. Tiny. Now the model says 0.1 confident and wrong. Loss negative log or 0.1 to 0.3. 23 times bigger. Cross entropy punishes confident mistakes brutally, and here's the full circle moment. This formula came from Information Theory Unit 1 and Minimizing it is Maximum Likelihood from Part 1 of this unit. 3 chapters, 1 formula. And now the star of the show: backpropagation, the error flowing backward. The setup: a fresh network has random weights, so it predicts wrongly. The gap between actual and predicted is the output error measured by the cost function. Backpropagation takes that error at the output and propagates it backward, layer by layer, to the input, computing, along the way, the gradient of the cost with respect to every weight. The engine underneath is the chain rule from calculus, and the back to front order lets each layer reuse the computations of the layer after it. That reuse is why it's fast. My favorite picture: a factory line produces a defective toy. You inspect the final product, then walk the assembly line backward, asking each station, how much did you contribute to this defect, and adjusting each accordingly. 1 clarification: exams love backpropagation is the gradient calculator. The actual learning rule using those gradients is gradient descent. Next slide. Gradient descent: using the gradients to actually learn. 2 ingredients decide everything. Ingredient 1, direction. The gradients from backpropagation tell us which way is uphill. We go the other way, the negative gradient, the decreasing slope, toward the minimum of the cost function. Ingredient 2, STP size, the learning rate. How far do we move per update? The source book's game: you're on a mountain, blindfolded, and must reach the lowest point. What do? Feel the ground, find where it descends, step that way, repeat. That's the entire algorithm. Direction from feel the gradient. Stride from caution, the learning rate. The update rule on screen: W new equals W old minus eta times the gradient. It's the same rule from Unit 1, nothing new to memorize. The only novelty is where the gradient comes from, backpropagation through the whole network. Let's watch one full descent step by step on the cost curve. 1. Initialize a random weight, a random starting point on the curve. 2. Take a step downhill, the gradient gives the direction, the learning rate gives the size. 3. The update formula produces the new weight. 4. Repeat step after step, walking down the curve. 5. At the minimum, we've found the weights with minimum cost. The model is trained. Vocabulary: 1 full pass through the training data is an epoch. Real models train for tens or hundreds of them. And notice how part 1 returns WHEN. Do we stop iterating? Exactly at the good fit sweet spot, early stopping, watching the validation curve. And each step's gradient can come from all the data, one sample, or a mini batch. Unit 1's 3 variants apply verbatim. The whole course is one connected story. The final quiz of the unit: the training loop itself. Put these in the correct order. 1. Compute loss. 2. Forward propagation. 3. Update weights. 4. Backpropagate gradients. Option A, 1 2 3 4. Option B, 2 1 4 3. Option C, 2 4 1 3. Option D, 4 2 1 3. Think about what each step needs from the step before it. Can you compute a loss before predicting? Can you have gradients without a loss? Pause and sequence it. The answer is B, forward propagation, then loss, then backpropagation, then update. The logic is a dependency chain. You can't compute the loss before you have a prediction, so forward comes first. You can't get gradients without a loss to differentiate, so backprop follows loss. And you can't update weights without gradients, so the update comes last. Each step feeds the next, no other order is possible. Say it like a chant: forward, LOSS, backward, UPDAT, then repeat epoch after epoch. And if you can also name where the learning rate acts, the update step, and where the chain rule lives, the backward step, then congratulations, you own the mental model this entire unit was built to give you. Let's gather the 10 takeaways or Unit 2. Try to beat me to each one. Generalization: perform on unseen data, that's the goal. Overfitting: low bias, high variance, great on train, poor on test. Underfitting: high bias, poor everywhere. Hyperparameters: chosen not learned, tuned on the validation set, never the test set. Point estimation: theta hat from data, its quality is bias plus variance. MLE versus Bayesian: data only versus prior times likelihood. Why deep learning: 8 challenges from complex data to compute arriving. The neuron weighted sum plus bias through an activation. The XOR lesson: hidden layers re-represent data until it's linearly separable. And the training loop: forward loss, backward update. That chant is deep learning. 10 cards, 1 unit. If each triggers a paragraph in your head, you're ready for the exam and ready for Unit 3. Resources to go deeper in this unit has the best free ones in the field. The textbook, chapters 5 and 6 of Goodfellow, Bengio and Corville, free at deeplearningbook.org. For pure visual joy, 3 blue 1 brown's videos: But What is a Neural Network? And his backpropagation explainer. The best animations of this material ever made. But my top recommendation for THIS Unit: TensorFlow Playground, playground.tensorflow.org. A neural network in your browser, no code. And here's your homework: load the XOR-like dataset, remove the hidden layer, watch it fail. Then add 2 hidden neurons and watch it succeed. The 1969 crisis and its solution reproduced by you in 60 seconds or clicking. Then, if you're feeling brave, implement XOR in 25 lines or NumPy. The day your own code learns XOR is a genuinely good day. And that's Unit 2 complete. Look at what you can do now: diagnose a model's failures from 2 numbers, explain estimation from both the frequentist and Bayesian views, and narrate every step of how a neural network learns, from the hot pen reflex to the weight update formula. Next unit we take our working network and confront its dark side. It can memorize anything including noise. Unit 3 is the complete toolbox for making networks learn instead of memorize: regularization plus the optimizers, like Adam, that make training fast and stable. Revisit the 4 quizzes in a few days, play with TensorFlow Playground, and I'll see you in Unit 3. Thank you for learning with me. If this lecture helped you, do like, share and subscribe to Shri Tech Bytes for more lectures like this one. See you in the next video.